All right, so first let's talk about relations, because functions are just a certain kind of relation. Okay, there are some constraints on a function, but a function is also a relation. A relation simply describes how one set of things or values maps or relates to another set of things or values. Okay, so it gives us the definition for how two sets of things relate to each other. All right. So some examples are the relationship that pairs people with their birthdays. That's a relationship. So we can say, for Janelle, the birthday is 8th February, and for Tegan, the birthday is, and for Jack, the birthday is, and for, so we can just have a relation that's non-mathematical, that just relates one set of things to another set of things. In the case of that example, it's people to their birthdays. In a math sense, we could have a pairing between some set of numbers and the result of multiplying those numbers by 2. So if we said we have a set of numbers 1, 2, and 3, we could define a relationship on the set S. That's what that notation is. A relationship on the set S in which we have S times 2. And that relationship then would be defined as this set with the number S, like 1, and it multiplied by 2. So that's one pair in that relationship, which is defined as the value times 2. So for 2 in our set S, the value would be 4, because 2 times 2 is 4, and for 3 in that set, the value would be 6. So if we said the relationship on S, where we have S times 2, then the set that's defined by that relationship would be this set with these pairs of numbers. Okay? So what is a function? Well, a function is a relation with the condition that each element in the source set maps to only one element in the result set. Okay? So for each element in the source, there's only one possible output when we define this relationship on it. So said another way, a function takes inputs and produces a single output for each input, like in functional programming. If we define a function, for any input we give that function, we expect a single distinct output. It should only ever output this given this input. Okay, so in functional programming, we define functions in the classical sense of what a function is. We're defining a relationship between inputs and outputs where each input produces a distinct output for that input. Okay? So there's some terminology here that you need to be familiar with. When we're talking about the set of inputs that are involved in this relation or function, we call that the domain. The domain is the set of possible inputs, all possible inputs. And the outputs that we get when we apply that relationship, that relation or that function, the outputs we get are called the range. Do you guys remember that from school, the domain and the range? Does this bring back some memories? So a lot of times we'll see functions expressed as f of x. Do you remember that? Where x is the element from the domain, and we apply the function to that element, and we say the result of that, applying the function to that element is f of x. And the result of applying that function to that element from the domain gives us a value in the range. So let's look at some other depictions of this. So these are examples of functions. So on the left, we have a function f of x, so a function on x, where where the function is defined as x times 2. And we're limiting the domain. We're saying that the domain is where x is an integer that's between 0 and 5, so greater than 0 and less than 5. And that's defining our domain. So our domain then is defined as the numbers 1, 2, 3, and 4. Does that make sense? Right? And so if we apply that function to each value in the domain, then we get the range. So we get a single output for each input, and That's the domain is the set of inputs and the range is the set of outputs. Okay? Now on the right side, we also have a function. In this function, we say the function is x squared. And we're saying x is an integer between -3 and 3. So greater than -3, less than 3. That means our domain, our set of inputs, is -2, -1, 0, 1, and 2. Yeah? And if we apply that function x squared, then we get for both -2 and +2, the output is 4. This is still a function because even though we have two inputs mapping to the same output, for each input there is only one output, right? So if I square -2, I always get 4. I never get anything else. It's always 4. So that means that this is a function, okay? Now, a lot of times in mathematics, when you see a function defined, the domain might not be limited that way. You know, we just say for every x, that's an integer, or for every x that's a real number, we're defining this function, x squared, right? And we can't, you know, in finite terms write out the domain in the range, but we can understand what those things are, right? And we might consider applying that function to only certain values of x. It depends on the application. But this is just another way to look at what a function is. So is that clear, the difference, what distinguishes a function from... A function is also a relation, okay? But it's just a relation with this special condition. So this one's not a function. If we said we had a relation where x is less than y, and x and y are between 0 and 5, okay, and x and y are integers, then our possible x's are 1, 2, 3, and 4, and our possible y's are 1, 2, 3, and 4. And if we apply that function to this set of inputs, so we say 1 is less than 2, 3, and 4, right? And 2 is less than 3 and 4, and 3 is less than 4. This is not a function, because for any particular x we consider, there are multiple possible y's. Okay, so this is a relation. We can describe a relation between x and y where we say x is less than y, but that's not a function. Okay, does that make sense? All right, so let's talk about some properties of relations now. And there are 3 properties that we're going to talk about. 3 common properties of relations. And the first one is reflexivity, a reflexive relationship. So, a relation is said to be reflexive, or x relates to y in a reflexive relation if and only if x equals y. So reflexive means that when for all elements in the domain, the relation will pair each element with itself. So an example of a relation that's reflexive is equal to, because every number is equal to itself. So if we defined a relation equal to, and then we had some domain, some set of values, like we said 1, 2, and 3, then for every element in that domain, 1, 2, and 3, we can say that it equals itself. So the pairs in that relation, if we had the set 1, 2, and 3, the pairs that result from that relation are 1 and 1, 2 and 2, and 3 and 3. So for every possible element in the domain, we can say it equals itself. So that means it's a reflexive relation. Okay? Sometimes we'll see a set defined as a particular domain. And we have some relation defined, and we know the result of that relation, the resulting set of that relation. And we can just look at the result set and look at the domain set, and we can say, okay, this relation is reflexive if for every element in the domain set, I can see that it's paired with itself. Okay? If that's true, then R, this relation, is reflexive. Okay?
Are there reflexive relations other than equal
In mathematics, there are. I don't think that there are. No. So you can say the relation knows in non-mathematics, like A knows B, is reflexive because everyone knows themselves. Maybe they do. Maybe that's a philosophical question. But you could say, that relation knows is a reflexive relation. So these concepts of relations and properties of relations do come up in philosophy and logic too, and not just mathematics, okay? And it's really about, and the properties are the same across all those domains. Yeah, I didn't want to say domains, I was trying to think of another word. All of those disciplines, fields, yeah. All right, so another property of relations is symmetry. And the property of symmetry says that x relates to y. If x relates to y, that implies that y relates to x. So, for example, non-mathematically, cousins is a symmetric relation. Because if I'm your cousin, you're my cousin, too. Right? You could also say nose. Maybe you could say nose is a symmetric relation. If I know you, then you know me. Maybe that's not true. That might not be symmetric. Maybe I'm just a stalker. Maybe I'm just a stalker. Okay, but cousins is a good example of a symmetric relationship. Or we can have a particular set defined, like 1 and 2. And if we have a relation that includes 1, 2, and 2, 1, then that relation is symmetric. So an example of a symmetric relationship equals would also be symmetric. If one thing equals another thing, then that thing equals the first thing. So you could say that that's also symmetric. Trying to think of another mathematic example that's symmetric.
So let's say you've got the numbers 1 to 10.
Yes.
And then on the other side you've got 1 to 10, but just mixed up.
Yes.
Is that the same?
So the thing is, you have to consider what the relation defines. So a relation is always going to define a set of pairs. Okay? It always defines a set of pairs. So for example, in the cousins example, if I have Ted and Susan and Bob, then if the relation is cousins and I look at two people at a time, Ted and Susan, if they're cousins, then they're in that relation as a pair. Ted and Susan are defined by that relation cousin. And if Ted and Susan are defined where Ted is Susan's cousin, then it's always true that Susan is also Ted's cousin. Mm-hmm. So we always have both of those pairs in the resulting relation set. Mm-hmm. Mm-hmm. Okay? So we have to consider how the relation defines how these things relate to each other.
Sure.
Okay? I don't think I can think of another mathematical example of symmetric. If somebody else can, tell me. Greater than, less than, divisible by, I don't think so. All right, transitivity is a little bit easier to think of examples for. So transitivity is x relates to y. If x relates to y and y relates to z, then x relates to z. Okay? So this property holds when for all elements in the domain, when that relation is applied, if it pairs x and y and it also pairs y and z, I'm saying z, I just wasn't aware of that, then it also pairs x and z. So less than or equal or greater than or equal are transitive relations, because if 1 is less than or equal to 2 and 2 is less than or equal to 3, then 1 must also be less than or equal to 3. Yeah? So less than or equal, even strictly less than or greater than, are transitive relations. Right? Now, less than or equal is also reflexive because equal is in there. So if I took any numbers like 1, 2, and 3, and I say, okay, less than or equal, I can put in that pair 1 and 1, 1 and 2, 1 and 3, yes? And I can put 2 and 2, 2 and 3, and I can put 3 and 3. So for each number in the domain, I have the number paired with itself. That makes it reflexive. And for each number in the domain, if I pair one number with another, and that second number with a third number, then I also pair the first number with the third number. So that makes it transitive. So these are not always easy concepts to understand. And what you need to understand about them is you need to understand what kind of relationship less than or equal, and greater than or equal are, what properties those relations have. Is it clear to everyone why those are symmetric and transitive? I'm sorry, not symmetric, reflexive and transitive? Is it clear why less than and equal, greater than or equal are? All right, I'm going to write something on the, let's just do it on here. Do it on here. So it can be on the screen. So if I've got, let me make the font bigger. If I have some set of numbers, okay, and this would be true for any set of numbers, and I say that my relation is less than or equals, okay? So for some value of s, like s 0, what this would mean, I'm just trying to think about how to write it so it's less confusing. If my relation is less than or equals, then what that means is if some s0 is less than or equal to s1 and s1 is less than or equal to s2, then s1 must be less than s0. Thanks. I was like, wait, what happened? S0 must be less than or equal to s2. Okay, so this is transitive. And the reflexive property, it is reflexive. It is. So if S0, then S0 equals S0, basically. So if we have an S0 in there, then it equals itself. Okay, it shows up in the relationship. So because if we apply this less than or equal to this set, what is the result that we get? R would equal, if I apply less than or equal, can I put 1 and 1? Can I say 1 is less than or equal to 1?
Yeah.
It is, so that belongs in the relationship.
So
Can I?
Belongs in the relationship.
That's
It has
right.
that property.
That's right.
So even though you have like 2 and 1, and
Doesn't
3 and
matter.
1, it doesn't matter.
Doesn't matter.
1, 1, 2, 2, 3, 3.
That's
4,
right.
5, 5,
That's
5.
right. Can I say 1 is less than or equal to 2?
No.
Less than or
Less than
equal?
Yeah.
Yes. So 1 and 2 go in this relationship as well, because 1 is less than or equal to 2. Can I say that 1 is less than or equal to 3?
Yeah.
So 1 and 3 are also in this relationship. Can I say 1 is less than or equal to 4? So 1 and 4 are in this relationship. 1 and 5? Also in this relationship. Now we go to 2. Can I say 2 is less than or equal to 1? Nope, so it's not in this relationship. Okay? Can I say 2 is less than or equal to 2? Yes, so it is in this relation. 3? Then it's in this relation. 4? Yep. 5? Okay, and then we go to 3. Is 3 less than or equal to 1? Then it's not in this relation. Less than or equal to 2? Not in this relation. Less than or equal to 3? It is in this relation. Okay, does this make sense so far? Less than or equal to 4? It is. And 5, right? And then what do I have for 4? 4 and 4, and 4 and 5. And then for 5, 5 and 5. And this set makes up, this describes this relation over this domain. Okay? This set describes this relation over this domain. Now, I can look at the set that describes this relation and determine if it has the properties of reflexivity, symmetry, and transitivity. And the way that I figure that out is I look at the numbers, and for reflexive, it says that if there's a number in the domain, I must see it paired with itself in the relation set. So for every number in this domain, do I see it paired with itself? Yes. I have a 1, 1, and a 2, 2, and a 3, 3, and a 4, 4, and a 5, 5. That means this relation is reflexive. Okay? Symmetric says, if in my relation set I have A paired with B, I must also have B paired with A. So if I've got 1, 2, I must also have 2, 1 in the relation set. Is that true? No. So this relation is not symmetric. All right? In order for it to be symmetric, I must see the reverse pairing for every pairing that I have in the set that describes this relation. Transitive says, if I see A paired with B and B paired with C, I must also see A paired with C. Is that true in this relation set? So I've got 1 paired with 2, and I have 2 paired with 3, and I also have 2 paired with 2, right? So if I just look at 1 paired with 2, I have 2 paired with 2. Do I also have 1 paired with 2? Well, yeah, I do. That's the one I started with. Do I also have 2 paired, I have 2 paired with 3. Do I have 1 paired with 3? Yes. I have 2 paired with 4. Do I have 1 paired with 4? Yes. I have 2 paired with 5. Do I have 1 paired with 5? Yes. And that's true for every element in the domain, isn't it? And that's because, and we can, if we think about it outside of this notation, less than or equal, or just less than even, yes? If one number is less than another number, and that second number is less than a third number, then we understand intuitively that that first number must also be less than the third number, right? So we can kind of intuitively understand that less than or greater than is a transitive relation. It has that property. But if we write out the set, we can see it too. So there's 2 different ways. The kind of intuitive way, what we understand, just sort of because we've been alive and using these concepts, and the more methodical way of looking at how the property is defined and making sure that we see the results in the set that reflect that property. So if I just gave you a set, a relation set, and I said R1 equals 2, 3, 3, 5, 2, 4, 2, 2, 4, 5, 3, 3, 2, 5. If I just did this first, Okay, so if I have this set, and what could I say are properties that this says it has? So first of all, is it reflexive? Is it reflexive?
No.
So first of all, tell me what the domain is. What's the domain that I'm working from? What is it?
2, 3, 4, and 5.
Now, how did we come up with that? How do we know it's 2, 3, 4, and 5?
Assuming that
Yeah, because those are the unique numbers that appear in my relation set. Exactly. So those are my domain. So if that's my domain, what is required in order for this domain to be reflexive?
2, 2, 3, 3, 4, 4, and 5, 5.
That's right. And I don't have all of those, do I?
No.
So that relation is not reflexive. Even though for some values that's true, it has to be true for every value in the domain in order for it to be reflexive. Is it symmetric?
No.
No. There's not even any symmetry in there, is there? There's no symmetry. But in order for it to be symmetric for every...
Technically, 2, 2 is symmetric.
Yeah, that's right. And 3, 3. Those are symmetric. That's right. That's right. But it's not symmetric because I have the pair 2, 3, but I don't have the pair 3, 2. Now, symmetric doesn't mean that everything has to be paired with everything else, both ways. It just means that if it's paired one way, it must be paired the opposite way too. Okay? Does that make sense? So if I have a 2, 3, I must have a 3, 2. But if I don't have a 3, 5, if I don't have a 3, 4, I don't have to have a 4, 3. Okay? There's no 3, 4 in here, so I wouldn't have to have a 4, 3, but for every pair I have in there, I must have the reverse pair in order for it to be symmetric. Is it transitive?
Yes.
So we can just look, right? So we have 2 paired with 3. So we look at what 3 is paired with. 3 is paired with 5, and 3 is paired with 3. But that's it. And 2 is also paired with 5. Yes? Okay? And then we have 3, 5, and 5 not paired with anything, so we're okay there. 2 is paired with 4, 4 is paired with 5, but 2 is also paired with 5. So we're okay there. 4 is paired with 5, but 5 is not paired with anything else. 3 is paired with 3, and that's okay, because as long as, and 3 is paired with 5, so there's no other 3 paired with something else that we have to make sure.
So it
Yeah,
has
so
to,
that's it.
for the transitive, it has to hold true for everything in these sets.
It has to hold true that if 2 is paired with 3 and 3 is paired with something else other than 2, then 2 must also be paired with that other thing.
Cool. So if we had a
Okay?
3, 6 in there, it wouldn't be transitive anymore unless we had a 2, 6.
That's correct. That's correct. So 2 is paired with 3. We have to look for any other pair where 3 is on the left and something other than 2 is on the right. Okay? Or something other than 3, sorry. Something other than 3 is on the right. So if A is paired with B and B is paired with C, then A must also be paired with C. Okay? The 2 outers also have to be paired together. So if I've got a 2, 3 and a 3, 5, I must also have a 2, 5. And if I have a 2, 4 and a 4, 5, I must also have a 2, 5. Okay? And as long as that property holds true for every element of the relation set, that we can say that that's true, then it's transitive. It has the property of transitivity.
Sorry, so you're taking the 2 outside numbers?
Yes.
Yeah, okay.
That's right. That's right.
Yeah.
So how come that is okay not to have a pair of 3 and 4?
So I would only need a 3 and 4.
Because you're saying A must be paired with B, and then A and B must pair with C, then A must pair with C.
So
then
actually
you
what
have
I'm not saying that A must be paired with B and B must be paired with C. What I'm saying is that if A is paired with B and B is paired with C, if those 2 relations exist in the set, then there must also be an A with C. So if there's an A and B and a B and C, if those 2 things exist, they don't have to, But if they do, if I've got an A and B, and then I've got a B on the left with another number on the right, then I must also have an A and C in here.
Oh, okay. So that
Okay.
doesn't apply with the where pairs with 3 on the left, because we only got 3, 3, and 3, 5. So
That's right.
3, 4 doesn't exist, and we don't have to worry about that.
We don't worry about it. Yeah, it's only if A, B, and B, C exist that we must have an AC also. Okay?
If you had just a relation that was 2, 3, and 3, 2, but you didn't have a 2, 2, would that not be transitive?
No. So 2, 3, and 3, 2 is symmetric.
It's symmetric, but
Yes.
if you didn't have the 2, 2 in there as well, it wouldn't be transitive.
So transitive says that it wouldn't be transitive because there's no C in that picture.
Yeah.
So, well, transitive says that if there's an AB and a BC,
So you need
so
the
where
three
AB and
values.
C are 3 different values,
They have to be different.
then you'd have to have an AC as well. Okay?
So if you had A, B, and
So
C,
if it's
and
missing
A,
though, if it's not there at all, if you've only had 2, 3, and 3, 2,
Is an empty relation reflexive and transitive? And
yeah,
symmetric?
I don't think that they are considered. I actually need to look that up. So there are probably applications where one or the other is true depending on how we're using this. Like it might be useful sometimes to consider that the empty set has those properties, and there might be other applications where it's more useful to consider that the empty set doesn't have those properties. So I think it probably depends on the application. Don't worry too much about that though, okay? Just given a set, you should be able to recognize does this relation set given the domain, because you have to know both pieces of information, don't you? Given the domain in this relation set, you should be able to tell if that is reflexive, symmetric, and transitive. And for general, you should also understand the properties of less than or equal and greater than or equal. Okay, what are the properties of those particular relations?
Well, does it happen that you'll see a relation just defined as a set like this? Sorry, I can't see everybody else. So like, in this case, what's sort of implied is a less than or equal to that's not really less than or equal to because there are some values missing.
Yes.
So is it common to see a relationship just defined as a set of pairs?
So probably in the applications of this, it may be possible that you have a set of data, like a domain set of data, and then you have some way that you're relating that data to each other that may not produce a comprehensive set of pairs. So maybe you're only relating some elements of the domain to other elements of the domain, maybe not everything to each other. And so the relation set that you come up with may not apply that relation to everything in the domain. So you could get, and then you may be interested in when this relation is applied, and this is the relation set that we get, does that show that the relation is transitive or symmetric? It's really hard for me to think of when you would apply this because I just haven't worked in those fields. It would be applied in things that I don't have practical experience in, so it's hard for me to think of like a good example. But I'm sure there are fields, since this is an area of study. I'm sure it's useful in those ways to something. Yeah, I couldn't tell you what it is. Probably not so important for you to understand generically as a programmer. It may be that you work in some particular field where you use this, but for a diploma of IT, it's something that you have to have a basic understanding of. And this is a very basic exploration of these concepts. So they're like whole courses on, properties of relations and understanding the implications of those properties and those sorts of things. So I started working on a worksheet for this. I will give it to you. There are some practice questions in that overall discrete maths review. Let me see if there's any more slides. I don't know if there are. One more slide? Oh, just resources. That's it. So there are some other resources that describe these things in different ways that might make it easier for you to understand if some of it's still not clear. And there is one functions worksheet that I put up there, I think. Was there one functions worksheet? So many directories. Yeah. Alright. So that's pretty basic. And then in the discrete maths worksheet,
Figure it out.
my Google Docs are getting out of control. I really need to do some organization. I just depend on the search all the time. I'm like, God, it's good enough. You can find anything that way.
Works for the internet.
It does, yeah. So there is a section in here. Here. Yeah, so there's just a little bit there. I'm going to make another worksheet with some more examples. I started working on it this morning, but I'm not done. And I'll pass that on when it's done. Any questions? Yes, Rachel.
That functions worksheet is just quickly put up. So it's
Yes.
it's the point of that exercise is to look at that's the input, that's the output, identify what will lead to those output to be the function.
No. So the point of this one is to look and say, does this is the domain, this is the range, does this represent a function, the relation that maps 3 to R, 5 to S, 3 to S, 7 to Z? Is this represent a function? It doesn't. And why doesn't it?
Because 3 points to R.
Because 3 points to 2 values. In order for it to be a function, each input can only point to one value. It's okay if two inputs point to the same value, but if one input results in 2 outputs when this relation is applied, that relation is not a function. Because the thing that distinguishes a function from other relations is that for every input, there is exactly one output.
So the left side can only have one line going from it.
It's possible that there's no output. That's okay too. There just can't be more than one. Yeah, because you could have an undefined output. So I always think of a graphical representation of functions because that's how I learned how to identify what a function is. So if you graph, because relations, paired relations can be graphed on a coordinate plane, on an XY plane, right? And for a function, you can't have 2 y's for any x value.
Can't do like that.
Yeah, so you can't have a parabola like this, but you can have a parabola like this that goes up or down, points up or down. That's a function. But there are places where that parabola is not defined. Like their inputs, their x's. No,
Well,
would
the
that be
same y
true?
value, yeah, because in a parabola you'll have like the same y value for 2 different x values.
A parabola that goes,
No,
yeah,
no,
a
it's
parabola that
normal,
goes
yeah,
this
okay.
way, yeah. Parabola that goes this way, for each x, there's only one y. But for each, for y's, there could be more than one x. And that's okay. That's okay. That's 2 inputs pointing to the same output. That's okay. That's still a function. But if you have one input that points to 2 outputs, then that's not a function. So this is one way to recognize if a relation is a function, is by mapping the inputs to the outputs like this, and seeing that for each input I only have one line going to the outputs. If I have more than one line going to outputs over here for each input, then it's not a function. Okay? Not a function.
is it a dumb question to ask? What happens if there's like an infinite loop? Like, is that something that features in this discussion?
It wouldn't feature in here. No. So here we're talking about.
You can have an infinite set though. Like
You can have an infinite set, but that's not necessarily an infinite. You definitely can have an infinite set. So if we talk about if our domain is all integers, then that's countably infinite, isn't it? It goes on the number line in both directions. Or even if we say the set is all positive integers or all natural numbers, that's an infinite set. So what matters is what relation are we defining on that set. So if we're defining the relation, for example, for each element in the domain of all integers, we consider, one element of that x, and we say our function f of x is x plus 1. So we're just going to add 1 to each element of the domain. Okay? Then that result set is also infinite. Yes? Because we can count from 1 to forever. And for every number, we can add 1 to it. And that gives us our result set. Right? So if our domain, if we say all natural numbers, so natural numbers start with 1. 1, 2, 3, 4, 5, 6, 7, 8, all whole numbers greater than 0. Then the result set for x plus 1 would be 2, 3, 4, 5, 6, 7, on to infinity. So those sets are infinite, but that is a function. Because for any number, if I add 1 to it, I'm always just going to get one result. I'm never going to get more than one result. So that means it's a function. Okay? But the example where I'm saying x squared, that's also a function, right? Because for each number, -1 squared, I'm only going to get 1. I'm not going to get something other than 1. Yes? But the other example I gave was one value is less than another value. X is less than y. Or it's really hard to define in mathematical terms. I mean, you can say x is greater than y, but you can't say like x plus 1, where you just apply something to the set and get something that's not a function. It's really tricky to talk about. But if I say the relation is x is greater than y, and my domain is 1, 2, 3, 4, 5, then for each x in that domain, then 3 is greater than 1 and 3 is greater than 2. See what I'm saying? 3 is greater than 1 and 2. So for the number 3, there's 2 possible outputs to that relation, which was what I tried to depict on this slide here. So this relation's not a function. X is less than y, where x and y are between 0 and 5. Because 1 is less than 2, 3, and 4. So there are multiple things that this 1 can be paired with in that relation set.
What happens if it's like a square root of a negative number?
A square root of a negative number, so let's just take a square root of a number, right? A square root of a number, like the square root of 4, we could say is positive 2 or negative 2, isn't it? So that's a good example. Square root where f of x is the square root of x, right? Then if x is 4, there are 2 possible outputs for that. And that's one of those parabolas that goes that way, right? So that's not a function. Because for each possible x, there's 2, the positive and the negative outcome. Do you have a question, Joe?
Let's see if we could get the link to this slide.
Yes. Yeah, sorry about that.
Will we get our
Did I post it
calculators
this
on the
morning?
test?
I think I put it in lessons this morning. Did I? Maybe I didn't.
How about the hard button?
Maybe I didn't. I probably did not.
Can Can we have calculators on the test?
Yes.
Graphing calculators?
You don't need it.
No, he just wants to look at the pretty graphs.
Yeah.
It won't help you. It won't help you to have a graphing calculator on the test.
You think? Do everything visually. I mean, I've got my TA84 testing stuff.
Well, they do on that.
I haven't made it yet, but it'll be coming.
It's a color calculator.
Okay, so let's just quickly talk about